right. Welcome to Power Machines in 6. Today's chapter is chapter 1. Chapter 1, we basically look at the revision of some of the key concepts or the basic concepts of N5. And that's all we'll be doing today. So today's going to be a fairly short session. I'm going to quickly go through some of the key concepts in chapter or in N5 that will be very important for the N6 course moving forward. Before I continue with that, does anyone have any questions or any specific concerns or areas of concern that they wanna? All right. So my opinion or assessment of N6 Power Machines N6 is that if you were able to go through the N5 course, you can definitely make it through the N6 course. Right. N6 is an extension of what we did in N5. Largely the same, actually. So in some sections, it dives a bit deeper. So if you remember correctly, N5, we looked at things like thermodynamics, we looked at air compressors, we looked at velocity diagrams, the diesel cycle, Otto cycle, all those things. And we're still going to look at that also in the N6 course, but maybe in more detail this time around. So same content, same material, same foundation, just maybe a bit more detail. All right, so with that being said, let me proceed. This is a textbook we use for N6. It hasn't changed. Still the same as what you used in, okay, you guys are probably first timers, so they haven't changed the textbook. It's the same textbook I've been using for years now to teach this course. So yeah. There are obviously other similar textbooks, N6 Power Machine textbooks, that you can use as a reference or as a guide when studying. Yeah, it's got, if you want maybe a different set of examples, you can check other textbooks on Paralegal. But this is the actual recommended textbook in your study guide. All right, so objectives for today, there's 3 objectives, like I said, is to revise the general properties of gases and gas laws, specifically Charles's law, Boyle's law, general and ideal gas laws. Right. We're also going to look at polytropic laws or polytropic expansion. We're going to look at adiabatic expansion, isothermal, which is also known as isochoric, or polytropic, is also known as, yeah, we're going to look at the different expansion conditions. So work can be done in 5 different conditions, right? So isothermal, adiabatic, general, polytropic, and constant pressure expansion or compression. And then we're also going to look at the entropy of gases. Maybe do 1 or 2 examples on that as well. All right, do you guys remember this table from from the N5 course? All right, cool. Perfect. I'm glad you do. I just want to share with you, it might help in your revision, but I just want to share with you something here. Oh, perfect, Michael. I'm going to share with you lesson 1, the first chapter of Power Machines N5, right? I just want to send it to the group chat as well. So this is the Power Machines N5 course. Chapter 1 of it is thermodynamics. So that's the basic concept. It covers the basics. It covers the basic concepts of pretty much the foundation of power machines is based on what you'll read here. So you'll see I gave you the different laws, Joule's law, Clausius's law, gave you examples of each, and then towards the end, there's a few examples that I've given. Right. And then I've also given you the table. This table is a bit neater though than the one so the one in the N5 is a bit neater. As you can see, you've got your isochoric, you've got your isobaric, which is your constant pressure. So your constant volume, constant pressure, constant temperature, adiabatic and polytropic processes. 5 processes as discussed. So if you want, you can go through the power machines N5 material as well. So anyway, for those who did power machines recently, you'll remember this table over here. It's got your 5 rows, your constant volume, your constant pressure, or on the other side, isochoric, isobaric, isothermal, polytropic, and adiabatic expansions, right? So depending on the question and what the question says, if the question says a gas is being compressed at constant pressure, you'll come to this column here, you'll come to the constant pressure column, or row rather. You'll come to this row and you'll read off all your governing equations to solve for whatever the question wants you to solve for, right? And then something that is important is to note is the difference between the general or the polytropic and the adiabatic laws, right? When you look at these two rows, they're basically identical. The only difference is that with an adiabatic process, Q is equal to 0, whereas in this instance, Q is equal to work plus delta U, whereas in this case, Q is equal to 0. But otherwise, all the other equations are the same. Polytropic and adiabatic are very similar to each other, just that with an adiabatic process, there is no heat that is added or rejected to the system. So with Q being 0, we know that work in this instance is going to be equal to basically this. Hello, can you all hear me? I think I had a connection loss, disturbance with my connection there. I don't know what happened. My apologies for that. So ultimately, these are the 5 conditions that exist for the compression and expansion of a gas. You always encounter one of the 5 conditions, and it's then up to you to come and look at the right column for that. What I've noticed is a problem, even in the N5 course, is that someone gets a question and they just use whatever equations they feel like using. It's important to read the question properly, as it will tell you exactly which sets of equations to use. Yeah, but we'll work through an example just now and just refresh your memory or jog your memory a bit. All right, so entropy of a gas, on the other hand, entropy is a thermodynamic property of a fluid that remains constant during a reversible adiabatic process. Other people define entropy as a measure of a quantity of energy in a system that is unavailable to do work. Right? Entropy increases as heat is applied, which is the reason why gas will have a higher entropy than a liquid or a solid. So a liquid has a higher entropy than a solid, but gas has a higher entropy than a liquid. All right, so that's how. And the formula for entropy is delta S is equal to the mass multiplied by the gas constant times the ln of V2 or V1 plus specific volume multiplied by ln T2 over T2 over T1, sorry. And the units for that are joules per Kelvin. All right, looking at this equation, okay, no, it's fine. All right, and then there's entropy at constant volume. The equation for that uses subscript CV or specific CV, whereas entropy at constant pressure uses CP. Okay, let's look at an example quickly. The example says calculate the change in entropy when 1.3 kilograms of gas, so you've got your mass over there, is compressed from P1 to P2 using this law, PV to the power of n is equal to C. All right, so if we go back to our table, right, where do we see PV to the power of n is equal to C? We see it in the general or polytropic equations, right? So we know this is the row that we're going to look at. These are the governing equations we're going to have to look at. Since they told us PV to the power of n is equal to C is the governing condition for this expansion. For this compression, sorry. So they tell us PV to the power of n is equal to C, where n is given as 1.2. The original temperature T1 is 15 degrees. CP and CV are this and that. So we know that CP or R is equal to CP minus CV, right? So we can calculate. If you look at this equation, what's the question says? It says calculate the change in entropy. So when you write out this equation, they've given us the mass. They've given us P1 and P2, which is not a P1 and P2 is not a variable in here, but we can use P1 and P2 using this. PVN is equal to PV1 is equal to P2 V2 to the power of n. We can use that to find V2 and V1. CV is given. T2, has T2 been given? T2 has not been given, so T2 we need to calculate as well. T1 has been given. All right, so what equations are we going to use to calculate T2? Let's go back to the column. So we're going to use these equations here. Calculate T2. We're going to use this to calculate V2. Or we can use this to calculate T2 actually, since we have T1. We have T1, we've got P2, we've got P1, we've got N. So we can rearrange this equation and calculate T2 from there. Right, once we have T2, we can either plug it into there and calculate V2, or we can use this to calculate V2. The choice is yours, basically. We can also use this, PV is equal to MRT. Once you've found V2, you can use that to calculate T2. I mean, since you've calculated your T2 in here, you can use this equation to calculate your V2. So it'll be P2 V2 is equal to MRT2. Right. So there's a lot of equations you can use to calculate the missing variables there. So, like I said, there's essentially how many missing variables in here? There's 1, 2, 3 missing variables, 4 missing variables. So this is a simple plug and play. We're just going to say 0.88 minus 0.63, give us the R value, and then we're going to use this relationship to calculate V2. So P1, V1 is equal to N R T1. You've got T1 and then you just calculated Rm was given, P1 was given, rearrange that, you find V1 is equal to X, and then you take that, whatever the value of V1, you plug it into there, you have V1, you have P1, you have P2, you rearrange, you solve for V2, now you have V2, and then you use P1, V1 over T1 P2 over T2 to solve for T2. And once you've solved for all these other missing variables, it's a simple case of plug and play into this equation and you've got your change in entropy. Does the process make sense, everyone? Good. All right, let's talk about some expectations before we get into the numbers of it. Let's talk about what we expect to see when we do such calculations. Right. Firstly, the gas is being compressed. They're telling us it's being compressed from 103.4 kilopascals all the way to 1,034 kilopascals. Right. So it's almost 10 times the compression. So what are we expecting for V2? We expect V2 to be significantly lower than V1. Right? Maybe even 10 times lower than V1. Because obviously when you compress something, you're reducing the volume of it. And what do we expect for T2? T2 we expect to be significantly greater than T1. Remember, when there's an increase in pressure, there's an increase in temperature. So those are the expectations. When we do our calculations, we're expecting to see a much smaller V2 and a much higher T2. And since it's a compression, we're expecting to see a negative value for entropy. So delta S will be negative X, Y, Z, whatever. It'll be a negative value since we're dealing with a compression equation. So those are the expectations. So now you know when you do your numbers and you calculate when you're doing your calculations, if you don't see what you're expecting to see, then you probably did something wrong. in there. All right. So first solution, like I said, calculating the R value. This one was simple and straightforward. And then you move on to find V1. You can use P1. V1 is equal to MRT1. Calculate V1. It's 0.933 meters cubed. From there on, you move on to find V2 using that given relationship, and you find the V2 value of 0.1369, which is in line with our expectations given the ratio of compression or the compression ratio. And then you move on to step 4, which is calculating the value of T2. T2 comes out as 422.59 Kelvin, which is higher than our T1 that was at 288 Kelvin, also in line with our expectations. And another way that you can use to calculate T2 is PV is equal to MRT equation, and you get roughly the same values. If you get 5.5 or 422.55 instead of 422.59, I'll still give you the answer, right? Then once you found all these variables, what do? You plug them back into this equation over here. I mean, into this formula over here. Right, step 5, now it's a simple plug and play. Mass was given. You just calculated this, you just calculated that, and that, calculated this, this was a given, and you end up with a negative 0.319 kilojoules per kilogram value for the entropy, which also, once again, is in line with our expectations, the negative value given that the gas is being compressed. Is everyone clear on that? Does anyone need extra clarity on any of the steps above? All right, let's look at a second example. This example talks about, okay, let's read the question first. Right. This example says 2.2 kilogram, 2.25. So that's the mass over there. That's P1. So they say 2.25 kilogram at P1 is 103.103 kilopascals, and the temperature of T1 is 10 degrees Celsius. It's compressed, right, isothermally. It's compressed isothermally to a pressure of P2 is 724 kilopascals. All right, so we go back to our table over here. This time around, they say it's compressed isothermally, so we're going to look at row 3. What I've just circled in the green is what we're going to use as governing equations. All right, since it's an isothermal compression, these are the equations we're going to use. All on the same page. So as you can see, guys, there aren't really any tricks when it comes to this. I guess the biggest trick is just reading the question properly, right? Trying to figure out what set of equations to use. Because what I've seen tends to happen is that someone gets a question like this, and the first set of equations that sort of seem to make sense is what they're going to be using. If the question says calculate the work that is being done in kilojoules, you'll see people using all sorts of equations for work, right? You'll see someone using this equation here for work. But if you look properly, you're actually supposed to be using these equations in here. In this row, the row of isothermal. Don't just take whatever's convenient for you or whatever's easier for you to understand. Take what you actually need to. It's an isothermal compression, so these are the only equations you're going to use to solve the problem. All right, they give us the value of Cp and they give us the gas constant R, and they want us to calculate the work done in kilojoules and then finally calculate the change in entropy. Okay, where do we start? Right, the first step, like I said, is to figure out which sets of equations to use. And then your second step would be converting the temperature, the 10 degree Celsius into into Kelvin. So you convert that to 283 Kelvin. And then your third step is writing out the equation for work, or the formula for work, right, for the work done. Once you've written that equation out, figure out if there are any missing variables in there. If there are any missing variables in there, your first step is to try and solve for those. Try and find the missing variables Then once you have everything, you plug it back into the formula for work and you calculate what that value is going to be. Fourth step, you write out the entropy equation, figure out if there's any missing variables in there either. If not, plug and play. If there are values that are missing or variables that are missing, you solve for those first, and then you come back and you plug it in and you solve. Does it make sense? So looking at the variables given here, what work equation are we going to use? The second one, MRT. So Michael says we're going to use MRT1 multiplied by the ln of V1 over V2, right? Well, the second equation, Mike, is actually the same as the first if you look at it properly. Since remember P1, V1 is equal to MRT1. So the first and second equations, these ones here, this and this basically give you the same solution. Since we have this P1 V1 is equal to MRT1. So you can substitute this portion in there with that portion in there, right? So ultimately, it all depends on the variables that are given in the question. So let's write them out quickly. We've got P1 V1 ln V2 over V1. Then we've got MRT1 ln V2. Okay, something's not right here. I'm not sure what's the correct one. Is it V2 over V1 or is it V1 over V2? Because these are supposed to be the same. Right? It's probably a mistake in the textbook. It's V2 over V1. And then we've also got MRT1 ln P1 over P2. So those are the three equations that we have for work, right? To calculate the work done for an isothermal process. Let's go back to the question and see what variables were given. They wanted to calculate the work done in kilojoules. Okay, cool. They've given us P1, they've given us T1, they've given us P2. So with that being said, what are we going to use? We're going to use MRT1 ln P1 over P2. Since we have P1, we have P2, we have T1, and we have R and M. So we simply plug and play and we get the value for work. Right, we use this one here. MRT1 ln P1 over P2, which is this one here. Right, you can see, guys, there's nothing to figure out. You don't need to figure anything special out. You just have to literally look at the variables that were given to you, go back to the table and figure out which equation you're going to use. So that's the equation we're using. The mass has been given, R was given, T1 was given as 10 degrees Celsius. You convert it to Kelvin, you get 283. And then you get P1 is 103 and P2 is 724. Right, so after that, you get a work value of negative 357.6 kilojoules for work. Right, simple as that. No tricks, no fusses. And then from there on, part 2 of the question was calculating the change in entropy. Once again, what do? You write the equation out for change in entropy. Right, you write the equation out, you figure out what missing variables do. And then you figure out what are the missing variables. And then you simply plug it in and you solve. All right, cool. That's it for today, guys. Simply stated, it was just a revision of what we had done in the N5 material, and it was just to refresh the basics. So that's it for today. Next week we're going to look at chapter 2. Right, so that's what we're going to look at next week, chapter 2. If you have some time, please prepare for that ahead. If not, that's also not a train smash. We'll go through it properly next week. Yeah, that's it. Enjoy the rest of your evening, guys.